Just as a point of sharing with you, I've been involved with CXL consortium from the beginning, served as the co-chair of the technical task force, and served as CXL president. I can attest to the great work that these guys have done with the rest of the community. Memory system and subgroup within CXL is very active. They tackle DRAM and device memory aspects of persistent and volatile memory. There are a lot of detailed discussions. Please join and contribute. Any questions? We have maybe a couple more minutes before the transition to the next topic.
If there is no question, then I'm going to ask a question.
Go ahead.
How many of you have actually got an opportunity to look into CXL Type 3 device implementation or even considering that? Anybody? Okay, so at least one. So. Okay. All right, good. Yeah, I mean, if you're interested and want to talk offline and share some thoughts, we can share our learnings also, because as Siamak was saying, I would say in Meta, we are among few front runners to actually implement a Type 3 device-based system.
That's right. Meta has been a promoter, member of the CXL consortium. It is very good to have technologies from different consortia and different SIGs, PCI SIG, JEDEC, NVMe, SNIA, all eventually show up within OCP community. Within OCP, we are a group of people who grab great ideas and put them into systems, build hardware, software, integrate them into solutions, and share them with others. That's the openness that OCP brings in. Okay, thank you very much. Appreciate it. Jayesh, please. Jayesh is going to introduce another topic that is based on many, many years of experience as well. I'm sure it will be a great discussion.
Thanks for the introduction, CMAC. Good morning, everyone. My name's Jayesh, and I'm the Senior Director for Platforms at Ampere Computing. I'm going to talk today about one of our systems, which is Mount Bonnell, and how pairing that with our processor from the Altra family actually provides a really compelling performance and goes along the story of how do we get to a carbon neutral future? How do we get to a point where we are able to actually provide the performance and yet lower the power consumption? And so I want to spend this presentation, take the time and share with you a little bit about Mount Bonnell, a little bit about the Ampere processor, and walk you through how even though performance and energy efficiency have always been at odds, how we were able to take our processor, how we were able to take some of the system level innovation and incorporate that and deliver something that actually can increase the performance and lower the power consumption when you compare that against legacy x86 platforms and systems. The processor that Ampere has in the Altra family are cloud-native processors. And so I'm going to spend a little bit of time talking about some of the metrics that we can use to demonstrate how these are more efficient, how they provide performance. And so in this session, I'll walk you through the processors, and I'll also walk you through Mount Bonnell. And some of the things that I'll highlight is how we're able to fit a lot of drives. The presentation before this one was about CXL, and so we are looking at incorporating and supporting some of the drives that may be out there in the future, whether it'll be as an add-in card or whether it'll be in the form of drives, whether cabled or risers. Some of the things that we have learned when we did Mount Bonnell, we're going to go back and contribute that to the DCMHS effort and then work with our other partners in the ecosystem and see how future technologies can also be incorporated. So when we started looking at Mount Bonnell, we actually went back and looked at, well, what's out there and try to understand why some of the decisions were made by other companies. And so we looked at Tioga Pass, which is a OCP submitted specification and design by Meta. And some of the things that drove them to that decision was obviously they were trying to get high performance. They were also trying to get 3 sleds in a 21-inch rack. And obviously, if you can fit 3 sleds in a 21-inch rack, you can fit 2 sleds in a 19-inch rack. And so we took some of that, and then there's a lot of work that OCP has done with the OCP NIC. It's still evolving, and there's discussion on what that would look like in the future to address some of the future needs. And so we paired that together and created Mount Bonnell. Diving a little bit more deep into Mount Bonnell, it uses the Altra family processor, as I mentioned earlier. It's 1 DIMM per channel, and it supports DDR4. The processor also has 128 PCIe lanes, so we're able to break those out into other connectors and also have the flexibility of it going to the risers and the OCP module. And as you can see, the board is much smaller, and as we worked on this a few years ago and now it's available in production, we started going down the modular path even more. So as Mount Bonnell has evolved into a following platform, and we've engaged into the DCMHS work group, we are actually working with the community and contributing our learnings back on how to make things more modular and ultimately provide the ability to mix and match and reuse some of the hardware. We created 2 SKUs. One is an E1.S SKU supporting 16 E1.S drives per node. So that's 32 E1S drives in a 1U. Each node has a single processor, and so together you get 256 cores in a 1U. The sleds are serviceable. It uses the OCP 3.0 NIC for networking, and the other SKU is a U.2 SKU. So when you talk about the system, the board and the chassis is one piece. The processor is the other piece, and that's really the elephant in the room. And so when you start looking at how many cores you can pack, comparing against legacy processors, Ampere CPUs have 2x the number of cores. So if you're looking to have a lot of cores in your data center, then that's one way to get there. The other piece to look at is the predictable performance. And where that comes into play is the Ampere cores are not hyper-threaded. They are dedicated cores. They are unique cores. And so a noisy neighbor problem or an issue where you have another workload running on, say, a hypervisor or a VM core, that's not going to affect the neighboring core. And so since each of our cores are unique cores, we don't run into that problem. The third vector is being elastic and scalable. When, with x86, because of hyperthreading, once the physical cores are consumed, the performance doesn't stay linear. Because the resources are used between the physical and the virtual cores, the resources are shared, and so the performance does not go up linearly as more and more cores are added. And that can be an issue, and that is an issue for a lot of our customers. That's an issue for a lot of the cloud service providers. With Ampere processors, as more cores are brought online, it stays linear. And finally, the other piece that we've been talking about and that has been a recurring theme in this conference is sustainability, is power efficiency. And so when we start looking at a lot of the workloads and looking at sustained TDP or average TDP, the average TDP is significantly lower with Ampere processors as compared to x86. And so the need for compute continues to grow. We see the market growing to 1.3 trillion by 2025. And so if we continue going down the current trajectory that we have, our power needs are going to double. Our real estate needs is going to increase by 60%. However, pairing up system-level innovation, pairing up more efficient processors like the Ampere processors, we can reduce the power footprint by 20%. So instead of it going up, we can actually reduce the power footprint. We can reduce the real estate needs because less servers are needed, because we have higher core count, we have higher performing processors. And so taking that together at a system level, what does that mean when you start looking at server count, and what does that mean when you start looking at the power consumption? You can actually get the same amount of performance by using 50% less servers, and you can get the same performance and reduce the power by 50%. And so by using this architecture, by using the Ampere architecture, you can reduce their server count and reduce power at the same time. So that's really compelling from a TCO perspective, and also from a CapEx perspective. So both your OpEx and CapEx can be reduced. And so I want to summarize by saying, when we looked at Mount Bonnell at a system level, we looked at what was available in the OCP community. We made some innovation around high-performance heat sinks. We improved the chassis in terms of serviceability and better venting. We incorporated the OCP 3.0 networking NIC, and then we're supporting the Ampere Ultra Max processor, which has a high core count and is energy efficient. So when we look at call to action and what we want to do, we want to continue innovating and looking at improving power delivery. We want to continue improving our thermals. And the learnings that we've achieved through the work on Mount Bonnell, we're going to be contributing that back into OCP through the DCMHS effort and through our participation in the DCMHS specification. Thank you.
Thank you very much, Jayesh. As Jayesh has stated, OCP works as groups. OCP server, underneath that we have the DCMHS, Data Center Ready Modular Hardware System, is a very active subgroup. Jayesh's team, Ampere, has joined that team. There was an earlier question about why did you pick this processor versus another processor? As long as the system is modular, the base specification allows different kinds of contributions into that system. And as we saw today, a compelling solution was available, and since the system, DCMHS, is modular, Jayesh's team found a way to plant a different solution into the same infrastructure. As long